What I'm about to tell you will come as a shock. Would you believe that if the solar system became too stable, we wouldn't exist? Sounds a bit absurd, right? But it's the truth. We tend to imagine stability as the natural condition of a successful system. A calm star at the center. Planets locked into predictable paths. A cosmic arrangement that has already settled into something finished and reliable. Diagrams reinforce this idea. They suggest that once order is achieved, survival follows naturally. But when you examine the solar system as it actually is, not as a schematic, but as a history, the pattern reverses. What stands out is not balance, but tension. Not permanence, but persistence under conditions that should have ended very differently. In the same system, entire oceans disappeared. Atmospheres thinned and failed. Internal engines shut down too early or continued running when they shouldn't have. One planet was tipped almost onto its side and remained intact. Another, so distant it receives little warmth, drives the fastest winds ever observed. A single massive world reshaped the fates of planets it never touched. Each of these outcomes can be explained on its own, but taken together, they don't describe a stable system. They describe one that never fully settled. This is not a story about how the solar system supports life. It is a story about how little margin there is for survival at all. Stability here is not the default, it is a temporary alignment. Existence is not guaranteed, it is conditional. Earth did not emerge because the system was orderly. It remained because the system was unstable in just the right ways, for just long enough. What follows is not a tour of planets, but an examination of near failures. 8 places where intuition breaks down quietly. 8 reminders that home is not something the universe provides, it is something that, briefly, has not yet been taken away. This makes survival feel like a narrow corridor that happened to remain open. But even corridors have an end, and the force that closes it is not a wandering planet or a stray comet. It is the star that makes every other story possible. The sun is the one constant we build our sense of normal around. It rises. It sets. It keeps time with light. It feels like the background condition of existence, not a character with an arc. But the sun is not a lamp. It is a body with a fuel supply and a history. And the most destabilizing fact about our system is that the same object that feeds life also guarantees that life's surface conditions cannot remain stable forever. It is easy to mistake that statement for drama. It isn't. It is mechanics. A main sequence star like the sun, which effectively means it is in the long. The stable prime of its life changes as it ages because the interior changes. Hydrogen becomes helium. The balance between gravity pressing inward and energy pushing outward adjusts. The core contracts slowly, heats slowly, and the rate of fusion shifts with it. On human timescales, the sun seems fixed. On planetary timescales, it is a moving target. And if you're trying to understand why Earth is a temporary exception rather than a permanent sanctuary, you eventually have to face the simplest pressure of all. The sun does not stand still. We talk about habitability as if it were a location, a comfortable ring around a star, a region where the equations allow liquid water, but habitability is more like a contract with an expiration date, written into the star itself. It is a narrow range of energy input where a planet can keep surface water without losing it to deep freeze or to runaway evaporation. That range shifts as the star brightens. Not quickly enough to notice, quickly enough to matter. When the sun's energy output rises, it does not simply make days warmer. It changes the entire planetary balance: oceans, clouds, atmospheric chemistry, the ability of rock to lock away carbon, the ability of a biosphere to keep oxygen cycling. Earth's current stability depends on feedback systems that can respond within limits. But those limits are real. A thermostat can only compensate so far before the external push overwhelms its range. At that point, What looks like a stable climate becomes a phase that ends. The ending does not arrive as a single catastrophic moment. It arrives as a drift. Ocean evaporation increases. Water vapor becomes more common, higher in the atmosphere. The protective cold trap weakens. Ultraviolet light breaks water apart more efficiently. Hydrogen escapes. The planet does not have to lose its oceans in an instant to be functionally oceanless. It only has to tip into a regime where losses outrun replenishment and where the surface becomes too hot for complex ecosystems to survive long term. This is the unsettling part. The sun can destroy habitability without ever becoming violent. It does not need to flare. It does not need to explode. It only needs to keep aging normally. The solar system's most inevitable disaster is also its quietest. And still, the same sun is the reason any of this could happen at all. Not because it is generous, but because it sits in a narrow category of stars that burn steadily for a long time. Many stars are more active, more volatile, more prone to violent outbursts that would make stable surface environments harder. Others burn through their lives more quickly, shortening the window during which complex chemistry can accumulate and persist. The sun has been steady enough, long enough, for Earth's slow processes to matter. Plate tectonics, ocean circulation, atmospheric evolution, the gradual construction of ecosystems that took immense time to become what they are. The sun didn't promise that window. It simply had it. You can see this duality even in the present-day numbers we use to describe it, because they read like fixed properties while hiding a story of change. The sun's effective temperature is about 5,772 Kelvin, a calm figure that suggests constancy, even though it represents the surface expression of a core whose conditions slowly evolve. Its nominal luminosity is 3.82, 8 times 10 to the 26th watts, a number that makes it feel like a stable machine, even though that output is the living consequence of fusion, the conversion of mass into energy, the slow reshaping of the star's internal structure. Its nominal radius is 6.95, 7 times 10 to the 8th meters, a clean measurement that implies a static sphere, even though the radius will not stay that way as the sun leaves its current phase. We name the sun with constants because we need constants to think. The sun itself does not remain constant. What happens later is not a sudden betrayal. It is the completion of the sun's nature. As hydrogen becomes scarcer in the core, the sun will begin to change its mode of existence. The core will contract and heat. A shell of hydrogen burning will dominate, and the outer layers will respond by expanding. The surface will cool as the star's photosphere spreads outward, and the sun will enter a phase where its size and brightness increase dramatically compared to what Earth has known. In that era, the inner solar system will no longer be a place where rocky planets can maintain the climates we associate with worlds. It will become a place where proximity is punishment, where orbits that once felt safe become too close to a star that has outgrown its earlier boundaries. The details of exactly how far the sun's outer atmosphere will reach and how individual planetary orbits will shift under mass loss and tidal interactions are complex. Models differ in specifics, but the conceptual outcome does not depend on the finest print. The inner system is not built for permanence. The sun's evolution will remake it. Worlds that were once heated from a distance will be heated from within the star's expanded envelope. Surfaces will be sterilized. Atmospheres will be stripped or altered beyond recognition. And even if a planet avoids being physically swallowed, it can still lose the conditions that make it a living home long before that final geometry is reached. It is also important to name what this does to the human idea of home. We tend to imagine that Earth is protected by being in the right place. But Earth is protected only by being in the right place at the right time, around a star, in a particular stage of its life. The habitability of Earth is not a permanent property of Earth alone. It is a relationship between planet and star. When the star changes, the relationship changes. Earth, does not have veto power. This is why the Sun's endgame is more destabilizing than any single planetary anomaly. Uranus can be tipped and still persist. Neptune can be cold and still violent. Mercury can keep what it should have lost. Jupiter can threaten and protect. But the Sun is the condition that underlies every one of those contradictions. It is the source of the energy that makes atmospheres dynamic, oceans liquid, chemistry active, and it is the source of the slow pressure that will eventually erase the narrow band of surface conditions life depends on. There is a temptation to treat the far future as irrelevant, because it does not press on our immediate lives. But the point here is not urgency. It is humility. The Sun's arc reveals that what we call stability is often a local illusion created by short measurement. On human timescales, Earth's climate can feel like a permanent setting that only occasionally fluctuates. On stellar timescales, Earth's entire era of surface life is a brief interval between states that are equally natural: too cold, too hot, too thin, too changed. And that recognition has a strange emotional effect. It does not make the present meaningless. It makes it more specific. It shifts home from being a guaranteed place to being a temporary arrangement held together by balances that do not last forever. It does not remove wonder. It changes the kind of wonder. The amazement is not that life exists. The amazement is that the conditions were allowed to remain coherent long enough for life to notice itself. This is the deepest contradiction the solar system offers. The Sun sustains life not as a gift but as a side effect of its current stage. It ends life not as a punishment but as a side effect of its next stage. There is no cruelty in it, and no kindness. Only continuity. The star does what stars do. Planets respond. Life, if it exists, adapts until it cannot. And so the ending is not a dramatic final scene. It is a slow tightening of constraints, a gradual narrowing of possibilities. Earth's oceans becoming harder to keep, Earth's atmosphere becoming harder to stabilize. Complex ecosystems losing the stable boundary conditions they rely on, the world still turning, still orbiting, still lit by the same star, only no longer living in a climate that can hold what we mean by life at the surface. The absurdity is not that the Sun will change. The absurdity is that the same star can be both the reason we are here and the reason we will not remain here indefinitely. We like origins that imply continuity. The Sun gives an origin that contains its own ending, written into the physics from the beginning. And when you hold that thought long enough, the solar system stops being a set of planets orbiting a stable center. It becomes a system where even the center is moving quietly, inevitably toward a future that does not include the version of home we recognize. Distance did not guarantee quiet, so closeness should not guarantee simplicity either. There is a point where the solar system stops behaving like a set of orderly rings and starts behaving like a story that was edited mid-sentence, with characters pushed onto stages that don't fit them. Mercury feels like that kind of character. Not merely the closest planet to the Sun, but a world that seems misplaced, like it belongs somewhere else, under different lighting, with different rules. It lives in a region where common sense expects the surface to be chemically exhausted, scrubbed clean by heat and radiation, until only the most stubborn materials remain. And yet Mercury carries ingredients that should not be comfortable there. It holds onto volatiles, materials like water or sulfur that vaporize easily, which, by intuition, ought to have escaped long ago. It even hides water ice in places where the Sun should have made the idea impossible. The planet does not just challenge our expectations. It makes us question why we were so confident about them in the first place. The simplest way to feel the wrongness is to imagine Mercury as a world without moderation. It has almost no real atmosphere, only a thin exosphere. Atoms temporarily lofted from the surface by sunlight, micrometeoroid impacts, and chemical sputtering. There is nothing substantial to distribute heat. Nothing to keep temperatures from swinging violently between day and night. There is no ocean to store warmth. No dense air to carry it. No clouds to soften extremes. The surface is exposed to the sun in a direct, almost intimate way, and exposed to space with equal honesty. It is the kind of environment where you expect anything light, reactive, or easily vaporized to be lost over geological time. But then you learn that Mercury is not chemically burned out the way we assumed. When we finally visited it properly, when we stopped treating it as a bright dot near the sun and began measuring it like a world, its surface composition didn't match the old script. Instead of being depleted of volatiles, Mercury showed evidence that it had retained more of them than expected. That discovery is subtle in the way that truly destabilizing facts tend to be. It doesn't look dramatic. It doesn't glow. It doesn't form an obvious landmark. It simply undermines the assumption that proximity to the sun automatically means a planet must become a stripped, purified remnant. It is tempting to treat that as a technical correction, an update to models, a footnote to formation scenarios. But the emotional weight comes from what the correction implies. If Mercury can keep what we assumed it would lose, then our intuitions about planetary aging are not reliable. Heat and time are not sufficient predictors by themselves. The solar system keeps teaching the same lesson. In different accents, outcomes depend on histories, not just locations. Mercury's structure deepens the unease. The planet looks like a piece of metal wrapped in too little rock. A body with a disproportionately large core. That alone suggests violence or anomaly in its past. Because ordinary formation in the inner disk does not naturally produce something so iron-heavy without some kind of sorting event, stripping event, or extreme temperature history that favored metal over silicate. When you look at Mercury's surface, you see a world that remembers impacts, scarps, and contraction evidence that the planet cooled and shrank, its crust compressing and breaking as the interior lost heat. The face is ancient, cratered, and yet not dead in the way a simple asteroid would be. It is a planet that had an interior story, and still has enough of one to generate a magnetic field. Another contradiction, given its size and apparent age. So why does it feel misplaced? Because every layer of Mercury seems to conflict with the simple idea of closest means most cooked. The more you examine it, the more it resembles a survivor of rearrangement, either a planet that formed under different conditions than its current orbit would suggest, or a planet that was modified so severely that its present form is not an honest reflection of its origin. One way to picture this is to stop thinking of planetary orbits as sacred. We grow up with the illusion that the solar system was assembled neatly and then locked into place. But orbital histories can be chaotic early on. Worlds can migrate. Resonances can shift. A planet can be nudged, scattered, or shepherded into a new region by the gravitational influence of larger bodies. Even if Mercury itself didn't travel far, the inner solar system was not a quiet nursery. It was a zone of collisions and near collisions, a place where the difference between this planet forms and this planet becomes debris could be a matter of timing and angle. In that context, Mercury's metal-heavy nature begins to look less like a mystery and more like a wound. The most discussed scenario is a grazing, catastrophic impact that stripped away much of Mercury's original rocky mantle, leaving behind a core-dominated remnant. Not a perfect head-on smash, but an event that peeled rather than pulverized. In human language, we want the event to be singular and decisive, a clean turning point. In reality, it could have been one major collision or a series of impacts that cumulatively changed the planet's ratio of metal to rock. The result is the same. Mercury looks like it lost part of itself and kept going. That kind of loss would also reframe the volatile paradox. If Mercury's present surface is not its original surface, if its crust and mantle were altered, mixed, recondensed, or partially rebuilt after impacts. Then, what Mercury should have retained becomes a harder question. A planet can lose material and later acquire or preserve volatiles in ways that defy naive expectations, depending on how the debris reassembled and what was delivered afterward. A world's chemistry is not simply what it started with, it is what survived, what returned, and what was never fully taken away. Mercury's polar ice sharpens this into something almost cruel. Even this close to the Sun, there are places where sunlight never reaches craters near the poles, where the geometry of the planet and the low tilt of its axis keep the floor in permanent shadow. In those pockets of darkness, temperatures can remain low enough for ice to persist for immense spans of time. The image is simple. A planet that seems condemned to heat still keeps cold rooms hidden at its edges. And inside them, water can remain stable. It feels like a loophole in the rules. But it is not a loophole. It is geometry. The universe doesn't need mercy to preserve ice. It only needs shadows that never break. And then there is the other side of Mercury's wrongness. Not only what it contains, but what it costs to reach. Traveling inward toward the Sun sounds easy in the way falling sounds easy. But in orbital mechanics, going inward is not simply going closer. It is a battle against speed. The closer you are to the Sun, the faster you move in orbit, and the deeper you are in the Sun's gravitational well. To rendezvous with Mercury, a spacecraft must shed an enormous amount of energy. It must reduce its speed relative to the Sun in a controlled way, like lowering yourself into a deep shaft without falling uncontrollably. This is why the path to Mercury required a choreography of gravity, assists 6 planetary flybys that slowly bled away velocity, using the solar system itself as a braking system. The engineering difficulty becomes part of the narrative. Mercury is not just physically close. It is dynamically difficult to approach, as if the planet is guarded by the mathematics of its own orbit. That difficulty matters because it mirrors the conceptual difficulty. We avoided Mercury for a long time, not only because of distance, but because it sits in a region where measurement is hard glare, heat, radiation, and the brutal requirement of orbital insertion near the Sun. When data finally arrived, it didn't reward us with a simple explanation. It rewarded us with a more complicated planet. Mercury's day length adds another layer of disorientation, not as trivia, but as a reminder that even time behaves strangely when orbit and rotation lock into unusual relationships. One full cycle of daylight and darkness on Mercury lasts 176 Earth days. That means day is not a daily rhythm. It is a prolonged exposure, a slow baking followed by a long release into cold. The surface does not experience quick resets. It endures extended states. If you imagine standing there, morning would not feel like a beginning. It would feel like a commitment the planet must keep for months. That kind of temporal extremity is another reason Mercury feels wrong. It does not offer the gentle alternation that makes environments feel stable. It offers long stretches of one condition, then long stretches of the opposite, as if the planet can't decide whether it wants to belong to heat or to cold. So Mercury becomes a world defined by contradictions that are all, in their own way, logical. It can hold volatiles because retention is not only about heat, it is about composition, replenishment, shadow, and history. It can keep ice because permanent darkness is a physical phenomenon, not a poetic one. It can be iron-rich because early systems are violent and impacts can reshape identities. It can be hard to reach because orbital energy doesn't care about our sense of near. It would do it. And behind all of it is the deeper, unsettling suspicion. Mercury may not have formed in the place where we find it now. Or if it did, it became something else through events that effectively moved it in composition, moved it in internal structure, moved it in what kind of world it could be. The solar system's inner region was a place where planets were not simply assembled, they were edited. Mercury feels like a draft that was revised too aggressively and then left in the final version anyway. The planet's average distance from the Sun is about 91 million kilometers. And even that number carries the wrongness if you let it. Not because it is small, but because it is definitive. Mercury lives that close, continuously, over and over, returning to the same brutal neighborhood and still not matching the simple expectations we attach to that neighborhood. It is a reminder that location is not fate. Not by itself. Fate is what happens when location collides with timing. Collisions, interior physics, and the messy aftermath of formation. Mercury is often portrayed as the obvious beginning of the solar system's story. The first stop, the nearest world. But it doesn't feel like a beginning. It feels like a consequence, a planet that ended up where it is. Not because it belongs there, but because the early solar system threw things around, and Mercury was the remnant that stayed on the wrong stage and learned to survive the lighting anyway. Further out from the Sun, a different kind of survival story unfolds, one so successful it's easy to mistake for a guarantee. Most people say Earth is special because it has water, but water is common in the solar system in the wrong places and in the wrong forms. Ice in shadowed craters, vapor in thin traces, ancient minerals that remember rivers the way bones remember flesh. The true oddity is not the presence of water. It is the endurance of surface oceans open, circulating, exposed to space and sunlight for a planet that has been alive to geology for roughly 54 billion years. In a neighborhood where planets lose water the way lungs lose air, Earth kept breathing. If you treat the solar system like a set of experiments, Earth is the one that should have failed for multiple reasons at once. Early on, the Sun was dimmer than it is now. By simple energy balance, Earth should have been locked in a global freeze. And yet geological evidence points to liquid water existing very early in Earth's history. Later, as the Sun brightened, Earth should have drifted toward a runaway greenhouse state, an ocean slowly turning into sky, water vapor breaking apart high above the surface, hydrogen leaking away into the dark. We know that pathway is real because it likely happened to Venus. It is not hypothetical. It is physics that does not care which planet it happens to. Earth has lived between these two failures, too cold to keep oceans, then too warm to keep them without falling fully into either. So you can start with the obvious protection, gravity. Earth is big enough that its escape velocity is not an afterthought, about 11.186 kilometers per second. That matters because the atmosphere is not a decorative layer. It is a weight. It presses on the ocean, keeping water stable at the surface, the way pressure keeps a liquid from turning to gas. At sea level, that pressure is about 101,325 pascals, and without something like it, liquid water becomes a temporary state, always trying to change phase. Earth's mass helps hold that pressure close. It is about 5.97, 2 times 10 to the 24th kilograms. Enough to keep a durable envelope of gas over long spans of time. Mars is smaller, so gases drift away more easily, and liquid water becomes less stable on the surface even before you consider temperature. On Earth, the atmosphere stays thick enough for long enough that water can remain water, not just briefly, but as a persistent surface condition. But gravity alone is not enough. A planet can be massive and still lose its water if the atmosphere is driven into the upper layers and broken apart. Ultraviolet light from the sun splits water molecules. The oxygen tends to stay behind, reacting with the surface. The hydrogen tends to escape. This is one of the simplest and most cruel paths for a world to dry out. You do not need a cataclysm, only time. A slow leak, a steady loss of the lightest atom. Earth has not been immune to this. Hydrogen escapes from our atmosphere today, The puzzle is that this escape has never become the dominant story. The reason it didn't is partly temperature, and partly the shape of Earth's atmospheric ladder. There is a region in Earth's atmosphere that acts like a cold trap. Water vapor rises, cools, and condenses before it can flood the upper atmosphere in large amounts. That sounds like a technical detail, but it is one of the quiet reasons oceans can exist at all. If too much water vapor reaches high altitudes, ultraviolet light can tear it apart efficiently, and hydrogen can be lost quickly. Earth's vertical temperature structure, and the way pressure and chemistry organize themselves with altitude, keeps most of the ocean from becoming a target. It keeps the ocean down, not permanently, not perfectly, but enough. Then there is geology. Earth is not a static rock with weather painted on top. It is a moving system. The surface is in conversation with the interior. Volcanoes release gases from the mantle. Weathering draws carbon dioxide out of the atmosphere by turning it into minerals. Plates subduct that mineralized carbon into the deep earth, where it can eventually be returned through volcanism. This is not a neat circle. It is a messy loop with delays and imbalances. But across long time spans, it behaves like a thermostat. If Earth gets warmer, weathering tends to speed up, pulling more CO2 from the air, reducing the greenhouse effect and cooling the planet. If Earth gets colder, weathering slows. CO2 can build up through volcanic outgassing, and the greenhouse effect strengthens again. The planet does not choose balance. Balance emerges because chemical reaction rates respond to heat, and because the interior continues to exhale. This is why Earth's oceans did not just survive, but stayed in a state that allowed complexity to accumulate. It is not only that water stayed liquid, it is that the climate stayed inside a narrow band where liquid water could persist on the surface for long stretches. Narrow, but not static. Earth has swung through deep, cold phases and endured hot periods where tropical regions likely felt like they were leaning toward a different future. Yet, in each case, the planet drifted back. Not immediately, not gently, but back. The existence of these recovery arcs is itself unsettling. It implies Earth has been close to edges multiple times and simply did not step over. A world can also lose water by hiding it, not in space, but inside itself. Water binds into minerals. It can be carried downward by subduction. It can be stored in the mantle in ways that do not resemble underground oceans, but still represent vast reservoirs. Earth is doing this constantly. Water is being cycled between surface and interior over geological time. That cycling is another form of endurance. Even if surface conditions fluctuate, the planet retains an inventory. It does not spend all of its water at the surface and then have nothing left to return. It has depth. It has storage. A planetary memory. None of this is guaranteed by distance from the Sun alone. Earth sits in a region often described as the habitable zone, but that phrase can make it sound like a safety label. It is not. It is a rough geometric suggestion, the range where liquid water could exist if enough other conditions cooperate. The Sun's light at Earth's orbit is not a promise, it is a pressure. At a distance of about 150 billion meters, the average incoming solar energy is about 1,361 watts per square meter. And that steady push nudges the system toward particular outcomes. Whether a planet resists depends on many small margins: mass, composition, internal heat, atmospheric chemistry, the presence of long-term recycling, and the timing of events that happened before the planet even had a stable surface. Timing matters more than we like to admit. Earth formed amid impacts large enough to melt surfaces and erase early histories. It likely experienced collisions that would have boiled oceans if those oceans existed at the time. Yet Earth has water now. That means either the water arrived after the most violent era, or it returned after being lost, or the losses were not complete. Each option is unsettling in its own way. If water arrived late, then oceans depend on a delivery schedule that had to be neither too generous nor too sparse. If the oceans were lost and returned, then Earth is resilient in a way that is hard to visualize, an entire ocean cycle recondensing, rainfall, rebuilding seas. If the oceans were never fully lost, then the early Earth stayed within a survivable thermal envelope even while being pummeled. In every case, the conclusion is the same. The endurance of oceans is not a static feature. It is the outcome of a history, and the sun does not stay quiet while this happens. It evolves. Young stars can be more active, emitting stronger flares and energetic particles, and that combination should have been a difficult environment for a young atmosphere. Earth's atmosphere remained. That implies additional shields and buffers were in place, including the fact that Earth's gravity and chemistry could replenish losses, and that the planet's interior behavior helped reduce direct stripping. Even if you postpone the details of magnetism, you can sense the central point. Earth's ability to keep an atmosphere is not a passive state. It is maintenance. Now add the most unnerving layer. Life itself became part of that maintenance, not as intention, not as a planet trying to stay alive, but as feedback. Life changes air. It changes what light does to the atmosphere. It changes surface reflectivity. It changes the chemistry of oceans. It changes how carbon moves. Oxygen, in particular, is not a stable gas around rocks and water. It reacts. If oxygen is present in large amounts, it usually means something is continually producing it faster than it can be consumed. On Earth, that something is life photosynthesis, over immense spans of time, coupled with processes that bury carbon and allow oxygen to accumulate rather than be instantly cancelled out by reaction. This is not comfort. It is another form of strangeness. It means Earth's long-term stability is not only a geological balance, it became a biological one. Once life emerged, the planet stopped being merely a stage and became a participant in its own conditions. Microbes changed ocean chemistry. Early ecosystems altered atmospheric composition. Over time, the presence of oxygen led to an ozone layer that filters ultraviolet radiation, changing the surface environment and the survivability of complex life. The planet's chemistry and biology became entangled. The biosphere did not just adapt to Earth. It began shaping Earth into a place it could continue to inhabit. But this entanglement is fragile. The same feedbacks that hold conditions within a range can overshoot, lag behind, or collapse if the underlying drivers change too quickly. Earth's history includes mass extinctions and long recoveries. It includes times when life nearly erased its own oxygen supply and times when greenhouse gases may have surged. A planet can keep its oceans and still punish everything living in them. So the statement, "Earth kept its oceans," is not a celebration. It is an observation with teeth. The oceans themselves are not inert. They absorb heat. They dissolve gases. They store carbon. They redistribute energy across latitudes. They act as an engine that smooths extremes. Without oceans, Earth would likely have sharper temperature gradients, more dramatic swings, a climate more easily pushed into failure. Yet, oceans also make Earth vulnerable in a different way. They are a vast reservoir that can be destabilized by changes in temperature and atmospheric chemistry. Warm the planet enough, and you shift evaporation rates, cloud formation, precipitation patterns, and ocean circulation. Cool it enough, and you trap water as ice, changing sea levels and climate feedbacks through reflectivity. The ocean is stability and risk in one body. If you step back, the endurance of Earth's oceans begins to look less like a simple trait and more like a long negotiation. The planet's mass holds air. The atmosphere holds pressure. The temperature structure keeps water from reaching the highest layers in dangerous amounts. The interior remains active enough to recycle carbon and water. The surface stays chemically responsive, and life, once present, becomes a chemical force that pushes the system into a new state and then keeps reinforcing it. None of these alone would be enough. Together, they have been enough so far. So far is the phrase that matters. Earth has not refused to dry out because it possesses a permanent right to oceans. It has refused because the conditions that would end its oceans have not yet won. The solar system does not hand out permanence. It offers intervals, even on Earth. Water has been rearranged. Climate has flipped. Continents have wandered. And life has been repeatedly reduced and rebuilt. We live in one configuration that happens to be stable on human timescales. The same system that kept oceans can also end them. If the balance tips and the feedbacks stop returning the planet toward the center. And the balance is not only internal, the sun is aging. Its output changes slowly, but it does change. Earth's climate thermostat has limits. It can compensate within a range, but it cannot negotiate forever with a star that steadily grows brighter. If Earth's oceans survived because of balance, then the uncomfortable question is not why the oceans exist. It is how long a balance can last when even Earth's axis, tilted by about 23.44 degrees, keeps changing what normal sunlight means across eras. While the central source of energy never stays the same. The balance is not only about climate, it's about retention. The sun guarantees an ending, but it also does the day-to-day work of erasing a world. Between a star and a planet, there is another layer of fate quiet, technical, and easy to forget until it fails. Most people assume life depends on water and air. That's true, but incomplete in the way a truth becomes dangerous when it sounds final. Water and air are not possessions. They are agreements a planet maintains with its environment. And the environment is not empty space. It is a stream, a constant outward breath from the sun, filled with charged particles moving fast enough to turn a planet's upper atmosphere into a coastline under storm surge. The solar wind does not need malice. It only needs access. Given time, it can steal the sky molecule by molecule, leaving behind a thinner world that still looks whole from far away. A magnetic field is what negotiates that access. Not a force field like fiction likes to imagine, but a shape in space that redirects charged particles away from direct impact. A bubble formed by invisible lines that the solar wind has to bend around. When the bubble is strong, the atmosphere is not exposed straight on. When it is weak, the atmosphere becomes a target, and the loss begins to resemble something physical. Ions swept away, hydrogen drifting off, the slow erosion of pressure that water needs to remain liquid on the surface. This is why auroras are not just decoration, they are leakage, made visible. A controlled collision, particles guided toward the poles where the magnetic field opens pathways downward, striking the upper air and forcing it to glow. The light is the evidence that something is hitting us all the time, and that the reason it isn't stripping the world clean is because most of it is being turned aside. A planet can look peaceful while its shield is doing constant labor. That shield is not built on the surface. It is built deep below it, in a place no organism can witness. Earth's magnetic field is powered by motion in liquid metal, a dynamo driven by heat, trying to escape, and by the planet's rotation, organizing that motion into something coherent. The key detail is not romance. It is structure. Earth's mean radius is about 6,371 kilometers. And far beneath that familiar crust, the planet becomes an engine rather than a landscape. The core is not a poetic center. It is machinery. The outer boundary of that machinery, where rock gives way to a metallic interior, sits at a core radius of about 3,480 kilometers. Inside that boundary, the rules change. Pressure rises. Chemistry becomes less intuitive. Heat moves differently. The outer core exists as a restless, electrically conducting fluid. And it is that conductivity that matters. Moving conductive fluid in a rotating body generates magnetic fields, not by intention, but by inevitability. It is one of those mechanisms that feels almost unfair. The right conditions produce protection as a side effect. And the side effect becomes the difference between a stable surface and a world that slowly loses the ability to hold itself together. Deeper still, the inner core begins at about 1,200 kilometers radius, a solid center inside the liquid layer. That boundary is more than a geological curiosity. It is part of what keeps the dynamo alive. As the inner core grows over time, slowly freezing out of the liquid outer core, it releases heat and changes buoyancy patterns, helping drive convection. The planet's shield, in other words, is tied to the planet's cooling history. It is not a permanent feature stamped into Earth at birth. It is an ongoing consequence of the planet still having enough internal energy to keep its deepest fluids moving. Once you see it this way, the solar system's tragedies become clearer without becoming simpler. Mars is not only dry because it is cold, it is dry because its protective bubble weakened. And once that happened, the planet's atmosphere became vulnerable to the sun's persistent stripping. The loss did not need to be fast to be final. It only needed to be continuous. And Mars shows the cruel part. You can have water. You can have rivers in your past. You can even have local environments that once looked promising. But without a long-lived shield, the planet's surface becomes a place where time is against you. The shield also changes how a planet experiences radiation. It does not block all high-energy particles, and it does not make a world safe in any absolute sense. But it reduces the direct coupling between solar wind and atmosphere. It buys stability. It buys retention. It buys the kind of long, boring continuity that complex life needs, not because life is fragile in a sentimental way, but because complexity takes time to build, and time is exactly what an unshielded atmosphere struggles to survive. This is why the word habitability is misleading when it's treated as a simple checklist. The shield is not on most checklists people carry in their heads. They imagine oceans and oxygen, a mild temperature, maybe a moon to stabilize tides. They don't imagine an invisible machine in the deep earth, turning slowly, maintaining a space around the planet that deflects what would otherwise strip it down. But once you understand what the solar wind is doing, the shield becomes hard to ignore. A world without it is not just different. It is on a clock that is set by physics, not by biology. And the unsettling truth is that shields are not guaranteed, even on planets that look promising. They depend on internal heat, on composition, on how a core cools, on whether a planet stays active enough to keep convecting metal. They can weaken, they can wander, they can collapse. A planet can keep oceans and then lose them later. A planet can start with protection and then become exposed. Nothing about the solar system suggests permanence is the default. Permanence is the rare outcome. And even then it is temporary. So when people look up and imagine life as a matter of finding another Earth, they often picture surface scenes, clouds, seas, continents. But the deeper question is quieter. Does that world have a shield? Does it have a working interior? Does it have an invisible boundary that turns the sun's constant pressure into a manageable noise instead of a slow theft? Because without that, water and air are not foundations. They are supplies, and supplies run out. Earth's shield is one of the reasons we can mistake our environment for stable. It keeps the loss slow enough to be invisible in a lifetime. It keeps the sky thick enough to hold liquid water at the surface. It lets the biosphere operate as if the sun were only light and warmth, not also a stream of particles trying to peel the planet over geological time. We owe much of our normal to a mechanism we cannot feel and rarely think about. The shield is not a miracle. It is a machine. And machines in the solar system do not run forever. To see what a world looks like after its machine has failed, you only need to look at the next world out. Mars is close enough to feel like it could have been a second attempt. Not an alien world in the distant dark, but a neighboring planet that once carried familiar ingredients, water moving across its surface, weather shifting over time, a horizon that was shaped by erosion rather than only by impact. When you look at Mars today, the surface is not just dry, it is exposed. The planet feels peeled, thin air, sharp temperature swings, a sky that can turn the color of rust because the ground itself is suspended in it. It is tempting to treat this as a simple story of a small, cold planet that never had much to offer. But the deeper discomfort is that Mars appears to have had a period when it offered almost everything a basic biosphere would need, and then it lost the ability to keep those conditions in place. This is not guesswork built from wishful thinking. Mars carries physical memories. Valley networks carved like old drainage systems. Deltas that looked like rivers once slowed down and dropped sediment into standing water. Minerals that typically form in the presence of liquid water clays. Sulfates, salts distributed across terrains that make sense only if water once lingered and reacted with rock. The planet does not merely hint at water, it testifies to it. And testimony is the cruelest kind of evidence, because it implies a world that once had options. Even now, Mars is not inert. The surface changes in ways that are small but persistent, like a body that keeps twitching after the mind is gone. From orbit, we watch storms build and fade, wrapping the planet in dust that can last for weeks and alter temperatures everywhere. Polar caps grow and shrink with the seasons, not only in water ice but in carbon dioxide frost that condenses and sublimates like a second, temporary atmosphere. In high-resolution images, there are avalanches at scarps of ice, dunes that migrate grain by grain, and seasonal streaks that appear on slopes and then disappear again. For a long time, those streaks were treated as possible signs of briny flows, liquid water persisting for moments under rare conditions. More recent work has pushed the interpretation toward dry processes, dust and sand moving in ways that mimic flow without requiring liquid at the surface. The effect is the same either way. Mars still rearranges itself. It is not a world frozen in time. It is a world that continues to change while refusing, almost completely, to be wet. That refusal is what makes the earlier evidence hard to sit with. Mars seems to have moved from a planet where water could shape landscapes into a planet where water cannot remain stable at the surface for long. The transition was not a dramatic explosion, it was a slow collapse of the conditions that make wetness normal. One of the more unsettling places to hold this thought is Eridania. Long before Mars became the planet we see now, Eridania was a vast depression that likely held a large sea. It is not the image of a small lake in a crater, but something broader, an ancient basin with evidence that water once stood there for extended time. Orbital measurements point to thick deposits rich in minerals that can form through hydrothermal reactions, warm water circulating through rock, altering chemistry, creating energy gradients. On Earth, environments like that are not just habitable. They are fertile in the deepest sense. Places where chemistry has multiple pathways, where reactions can feed on each other, where life can exploit the difference between what the rock wants and what the water allows. If Mars ever had a window for life to begin, Eridania is the kind of environment that makes the idea feel less like a fantasy and more like a missed outcome. And then you look up from that ancient sea and see the planet it became, cold, airless, scraped by radiation, keeping most of its remaining water either locked in ice or trapped in minerals. The paradox sharpens. Mars did not fail because it lacked a location with energy. It did not fail because water never existed. It failed because it could not keep the entire system running long enough for those local possibilities to matter. The usual explanation begins with size. Because size is not just a number, it is a schedule. Smaller planets cool faster. They lose heat more quickly. like a small ember that stops glowing while the larger fire still burns. In the early solar system, Mars had internal energy. It differentiated into layers. It likely had active volcanism. It almost certainly had a global magnetic field at one point, an invisible structure generated by motion in its interior. But that interior did not keep moving the same way forever. A planetary magnetic field is not a decorative halo. It is a consequence of a living interior, a core that remains hot enough, liquid enough, and stirred enough to act like an engine. When that engine runs, it produces a field that reaches into space and deflects charged particles streaming from the sun. When the engine stops, the planet is left exposed. Mars seems to have kept the engine running early on and then lost it. The evidence is written into ancient crust, remnants of magnetization in older rocks that imply a global field existed when those rocks formed, and a lack of similar signatures in younger terrains that suggests the dynamo shut down. No single line on a graph marks the moment. It is more like watching a heartbeat fade on a monitor and realizing afterward that the last strong pulse has already passed. Once the shield weakens, the atmosphere changes its relationship with the sun. The solar wind is not just light, it is a stream of charged particles. Over time, it can erode an atmosphere the way constant wind can erode stone slowly, relentlessly, without needing a single violent event. Molecules in the upper atmosphere can be energized and lost to space. Ions can be picked up and carried away. Ultraviolet radiation can break apart molecules, separating hydrogen that escapes easily from heavier atoms that remain and react. This is not a fast apocalypse. It is a leak that becomes destiny. As the atmosphere thins, surface pressure drops. That matters because water is not only about temperature, it is about pressure as much as heat. Reduce pressure enough, and liquid water becomes unstable. It tends to boil or sublimate rather than pool. Mars could still have ice. It could still have water trapped in the ground, but stable. Long-lived surface, rivers and seas become harder and harder to sustain. The planet crosses a line where wetness is no longer an ordinary state. The cold follows. With less atmosphere, Mars loses heat more easily, especially at night. Temperature gradients sharpen. Water that might have been liquid becomes ice. Carbon dioxide can freeze out as well, making the atmosphere even thinner, reinforcing the cycle. The planet can enter feedback loops where losing air makes it easier to lose more air, where losing warmth makes it easier to lose water from the surface, where the remaining water gets pushed toward poles or buried under regolith, out of reach of sunlight and biology. What makes this story feel brutal is how physical and indifferent it is. There is no moral lesson. Mars does not choose to become barren. The planet simply runs out of internal energy soon enough that the magnetic engine weakens. And once that happens, the external environment begins to take what is easiest to take. Mars is not being punished. It is being treated normally by the physics of exposure. And yet it is hard not to feel the tragedy in the timing. Mars may have had lakes and seas when Earth was still young. It may have had rainfall, erosion, sedimentary layers accumulating slowly. There may have been a period when a microbial biosphere, if it began, could have spread. But biology, if it ever started, would have been living on borrowed time without knowing it. The planet's capacity to protect its air and maintain surface pressure would have been waning underneath the surface. In the quiet cooling of the core, even the water that remains tells you the loss was not total, only decisive. Mars still holds vast ice deposits, especially in polar caps and in subsurface reservoirs. Some of the planet's water is locked into hydrated minerals bound into crystal structures, hidden in rock, where it cannot easily become part of a living cycle. If you add it up, Mars may still have enough water to cover large portions of the planet if it were all released, but it is not released. The planet keeps it in forms that are stable under the current pressure and temperature. Mars has water, and yet Mars is dry. That is another kind of contradiction. The ingredients can exist while the environment refuses to let them behave the way life would need. There is also the temptation to imagine that Mars's loss was inevitable from the beginning, that the planet was doomed by being smaller. But smaller does not automatically mean hopeless. It means less margin for error. It means shorter duration. It means that events that would be survivable on a larger world can become fatal on a smaller one. A giant impact, a change in mantle convection, a shift in how heat moves through the interior. Any of these could help stall or stop a dynamo. We do not need to believe in a single cinematic cause. The more unsettling possibility is that nothing dramatic was required. The engine could have shut down simply because the planet cooled. Gradually, as planets do. This makes Mars feel less like a failure and more like a warning about what habitable actually means. Habitability is not a place on a map. It is a duration. A planet can be habitable for a while and then stop being so. Not because it loses all water at once, but because it loses the ability to keep an atmosphere thick enough, long enough, to maintain stable surface conditions. In that view, Mars is not the planet that lacked what Earth has. Mars is the planet that had something like it, and then its clock ran out early. There is a particular kind of quiet horror in that. It suggests that life does not necessarily lose, because the universe refuses to provide the right ingredients. Sometimes life loses because the planet cannot keep the game running long enough, because the board itself shrinks beneath you, because the shield fades, because the atmosphere thins, because the interior stops feeding the surface. Mars feels like a world that once had a future that could have been ordinary, and then became extraordinary in the worst way, a planet that still shows signs of motion and history, yet is stripped down to the bare mechanics of survival with almost nothing left to survive for. And the most unsettling part is how simple the root cause can be. When you finally strip away the romance, Mars is a little too small. And the universe does not give extra time to small worlds. But perhaps it wasn't doomed by its size alone. Perhaps its fate was written by a neighbor so massive that its decisions become everyone else's biography. Jupiter is easy to describe as a planet and harder to describe as a force. It is not simply the largest. Its mass is the kind of presence that turns the solar system from a set of independent worlds into a coupled system, where one body can write consequences into places it never physically touches. Jupiter is about 317, 8 times the mass of Earth. And that number matters less as trivia than as a hint. There is enough gravity here to reorganize neighborhoods, enough to throw material inward and outward, enough to interrupt planet formation, enough to turn gentle accretion into scarcity. When a world carries that much mass, it doesn't just exist, it participates in every orbit near it, and many orbits far from it, like a slow-moving thought that keeps intruding into other people's lives. In size, it is almost absurdly excessive. Jupiter's equatorial radius is about 69,911 kilometers, which means the planet becomes a gravitational landscape on its own scale. A place where nearby can still mean thousands of kilometers of atmosphere and depth. There is no surface in the human sense, only layers transitioning into other layers, pressures that turn matter into unfamiliar behavior. You can look at the cloud bands and feel you are seeing weather, but you are also seeing the outer skin of an object that behaves more like a small star that never ignited than like a planet we evolved to imagine. And yet the paradox is not its bulk. The paradox is its role in the making of everything else. Jupiter sits at a mean distance of about 5.204 astronomical units from the Sun, far enough that it didn't become a rocky planet, close enough that it formed in a region where its gravity could reach inward and disturb the entire zone where terrestrial planets were still being assembled. This is where the solar system starts to feel less like a stable arrangement and more like a history shaped by near misses. Because Jupiter does not merely orbit, it shapes the space around it like a hand shaping water, pulling, scattering, and occasionally protecting by accident. There are ways to tell this story as destiny, but Jupiter is not destiny. Jupiter is contingency with weight. Early in the solar system, the disk of gas and dust was not a quiet background. It was the medium in which planets formed, migrated, and fought for orbital territory. In that environment, Jupiter likely did not remain where it is now. It interacted with the disk. It exchanged angular momentum. It moved. How far and how fast is still a matter of models. And the models still argue with each other. Not because the idea is weak, but because the early solar system was an environment where small differences compound, change a detail of the disk's density or viscosity, and the planet's path can shift. But the concept that matters is simple. Jupiter's orbit was not a fixed pedestal. It was a trajectory that could have carved the inner system into a different shape. This is where Jupiter earns its first title as destroyer. If Jupiter migrated inward far enough, it would have plowed through the region that later became the asteroid belt, scattering material, starving growing bodies, and leaving behind a zone that looks like it should have become a planet but never did. In many formation narratives, the asteroid belt is not supposed to be what it is. It's too empty for its location. It feels like a construction site abandoned mid-build. Jupiter can explain that abandonment without needing intention. Its gravity can clear, excite, and disperse. It can turn an orderly growth region into a collisionally violent environment where material fails to settle into one body. And if Jupiter's influence reached into the region where Mars was forming, it could have limited Mars's growth by disturbing the supply of building blocks, scattering them, ejecting them, or preventing them from accreting efficiently. Mars then becomes not a planet that failed for its own reasons, but a planet that was never allowed to become larger. A small world, not by fate, but by theft. In that view, Mars's later loss of atmosphere and water becomes entangled with Jupiter's earlier movement. Mars ends up too small, and later it cools too fast, and later its shield shuts down, and later it is stripped. The tragedy begins long before the planet becomes dry. It begins in the distribution of rock that never reached it. But if Jupiter were only a destroyer, we would not be here. That is the second title, and it arrives like a reversal that feels too convenient until you remember that the solar system doesn't care about narrative symmetry. The same gravitational force that scatters can also arrange. The same migration that disrupts can also seed. Jupiter's movement could have been halted and reversed by the presence of Saturn, through a gravitational resonance that changed how both planets traded momentum with the disk. The details of that dance are complicated, but the emotional meaning is sharp. If Jupiter's inward migration had continued unchecked, the inner solar system might have been stripped of the material needed to build Earth. If it reversed in time, enough material remained to allow the terrestrial planets to finish forming. In other words, Jupiter can nearly ruin everything without ever trying, and then save everything without ever deciding to. This is one of the most disorienting themes in planetary science. Life does not need the universe to be kind. It only needs the universe to be not too different for long enough. The line between no Earth and Earth exists can run through orbital resonances and migration endpoints that had no awareness they were shaping the possibility of biology. Jupiter's orbit itself carries that sense of long-term influence. It completes a trip around the Sun in about 86 years, which means it returns to the same regions of gravitational influence on a timescale short enough to matter for the architecture of minor bodies, but long enough to feel slow and monumental compared to our seasons. Each orbit, it is quietly working, tugging on asteroids, reshaping cometary pathways, stirring resonances that can destabilize or protect, depending on where you stand. Jupiter is not a single event. It is a repeating pressure, And because it rotates quickly, about 93 hours, for a full spin, it turns its own atmosphere into a display of differential motion. Bands, jets, vortices that can persist for long times. The rotation is not just a visual feature. It is a reminder that Jupiter is a fluid world where the line between weather and interior dynamics is not clean. What we see at the top is connected to what happens deeper down. The planet's presence is not only gravitational, it is energetic. It emits more energy than it receives from the sun. Not because it is burning like a star, but because it is still radiating heat from its formation and ongoing contraction. Jupiter is not just large, it is still thermally alive. This is part of why Jupiter is both threat and shelter. On the threat side, its gravity can inject objects into the inner solar system. It can destabilize small body reservoirs and send comets inward on paths that cross Earth's orbit. It can turn distant, harmless ice into a potential impactor. The same physics that lets it sculpt the early system continues to operate. Slowly. We tend to imagine danger as an anomaly. Jupiter makes danger into a background process. On the shelter side, Jupiter can also remove threats. It can capture comets. It can fling objects out of the solar system entirely. It can absorb impacts that might otherwise happen elsewhere. There is no guarantee it does more protecting than endangering. The balance depends on the population of small bodies and the architecture of orbits, but the capacity exists, and we've seen it in the most direct way a planet can demonstrate anything: by being hit. In 1994, a comet broke apart and struck Jupiter, leaving visible scars in its atmosphere. The event did not feel like a cosmic spectacle so much as a demonstration. Jupiter was not being dramatic. It was showing what it means to be the largest gravitational target in the neighborhood. It was also showing something quieter. Impacts that would be globally catastrophic on a rocky planet can become transient marks on a gas giant, visible for a time and then swallowed by circulation. Jupiter can take hits without being wounded in the way we understand wounds. That changes the emotional logic of threat. It suggests that in a system full of debris, a massive body can act like a sink, sometimes by deflecting, sometimes by ejecting, sometimes by absorbing. But even this protection is not a moral category. It is an emergent consequence of mass and location. Jupiter's surface gravity, at the level we conventionally measure it, is about 24.79 meters per second squared. And that figure isn't important because it tells you what you would weigh. No one is standing there. It matters because it indicates the strength of the gravitational field that bends trajectories. It is a measure of how hard Jupiter pulls on passing objects, how strongly it can rearrange paths, how easily it can turn a long-period wanderer into a near-term visitor. Jupiter's gravity is the reason comets can be redirected, for good or for harm, and the reason the inner system is never fully isolated from the outer. Its escape velocity is about 59.5 kilometers per second, which is another number that carries existential weight if you let it. Escape velocity is a threshold. Below it, things remain bound. Above it, they can leave. Jupiter sets thresholds for others. It decides what remains in the solar system and what gets thrown out. Not as a conscious gatekeeper, but as a gravitational filter that operates across millions of years. That filtering affects impact rates, delivery of volatiles, and the slow mixing of material between reservoirs. If Earth received water-rich material from beyond the snowline, Jupiter's migration and gravitational stirring are part of that delivery story. The oceans on Earth are not just a local feature. They are the result of a dynamic system that moved materials across zones that look separate on a diagram but are not separate in reality. This is the part that makes Jupiter feel like a god in the ancient sense, not benevolent, not malevolent, but too powerful to ignore, too entangled to simplify. It can starve Mars and help feed Earth. It can disrupt the asteroid belt and also stabilize certain orbital regions by creating structures that trap objects in resonant relationships. It can increase the flux of impactors and also reduce it by ejecting bodies that would otherwise remain to threaten the inner planets. It can do both because the solar system is not a machine designed for one outcome. It is a set of interacting masses where cause is rarely singular, and effect often has two faces. So when you hear that Jupiter nearly ruined everything and saved it, what that really means is that Jupiter sits on the boundary between different possible solar systems. If it had formed slightly earlier or later, if it had migrated slightly farther inward, if Saturn had not arrived in time to change the migration regime, the inner planets could have ended up very different or not formed at all in the way we recognize them. Earth's existence begins to feel less like an inevitability and more like a narrow corridor that Jupiter did not close. The unsettling thing is not that we can tell this story. It's that we can tell it and still not be fully sure which version is correct. Because the early solar system is a chaotic environment and we are reconstructing it from leftover evidence. We can simulate, infer, constrain, argue. We can build plausible histories that match what we see, but we cannot rerun the tape. Jupiter's true path is something the solar system remembers more clearly than we do, and yet the philosophical outcome doesn't depend on the exact path. It depends on the fact that such paths exist at all. Jupiter reveals that our home system was not assembled gently. It was negotiated by gravity, shaped by migrations, cut by resonances, and stabilized, not by design, but by the way certain accidents happen to counteract others. The planet that could have emptied the inner solar system also made the distribution of water and material possible in the form we inherited. It did not choose to spare us. It simply stopped where it stopped. Once you see Jupiter this way, the solar system becomes harder to romanticize. It stops being a calm neighborhood and becomes a precarious arrangement of outcomes, each dependent on bodies that did not care what they enabled. Jupiter is the reminder that the line between ruin and survival can be drawn by something as impersonal as orbital mechanics. And that saved can mean nothing more than not erased. Okay, if Jupiter's strangeness comes from the power it projects outward, the next giant comes from the engine it keeps hidden within. A world that looks orderly, yet runs on an energy source that sunlight can't account for. Saturn sits far enough from the sun that the light feels more like an announcement than a force. It arrives diluted, patient, almost reluctant. If you carry Earth's instincts out to that distance, you expect a weak atmosphere, slow weather, a world whose motion is driven mostly by inertia and not by heat. On Earth, the engine is obvious. Sunlight warms the surface. The surface warms the air. Differences in heating create winds, storms, pressure systems, circulation. It's a simple chain you can feel on your skin. But Saturn refuses that chain. Because Saturn refuses the main condition it relies on. There is no surface to heat the way a rocky planet does. There are cloud tops, and deeper layers beneath them, and deeper layers still. The place where ground would be is not a place you can stand. The usual rulebook doesn't merely fail. It has nothing to grip. And yet Saturn has weather. Not decorative motion. Not a gentle haze. Real dynamics. Banded winds. Persistent jets. Storms that appear and fade. Lightning that flashes inside clouds no human will ever touch. The contradiction is not that Saturn has weather. It is that the weather has the intensity of a system that should be receiving far more energy than it does. If sunlight is not enough, something else must be paying the bill. Cassini became the witness to that payment, not because it saw an engine directly, but because it spent long enough watching the patterns repeat and distort to make the conclusion unavoidable. Saturn is not being driven from above, it is being fed from within. On Saturn, the atmosphere is not a thin consequence of surface conditions. It is a thick, layered fluid that is itself the stage, the actor. And the curtain? The clouds are not painted on top of a world. They are the world's visible edge. When they move, you are seeing the planet's internal energy leak upward in slow, organized violence. The first clue is rotation. Saturn's day is short enough to force the entire atmosphere into disciplined motion, stretching storms into bands and sharpening jets into long, persistent corridors. One day on Saturn lasts 7 hours. That single fact changes everything. Rapid rotation turns atmospheric motion into geometry. It pushes flows into east-west streams, creates boundaries between belts, and makes weather behave less like a wandering chaos and more like a set of lanes on a highway that no one built. The planet's spin becomes a mold the atmosphere must fit itself into, no matter what tries to disrupt it. But rotation alone doesn't generate the energy to keep the lanes active. It only shapes whatever energy is available, and the energy is there. Somehow, despite the weak sunlight, Saturn carries internal heat left over from formation. But leftover can sound passive, like warmth trapped in a rock. Saturn's heat is not trapped. It is working. Gravity is still doing slow labor inside the planet, compressing material, converting potential energy into thermal energy. In a gas giant, contraction is not a dramatic collapse. It is a subtle settling that can continue for very long spans, releasing warmth as it happens. The planet is heavy enough that simply existing is an ongoing process, a continuous pressure that becomes temperature. Then there is separation. Inside Saturn, not all fluids remain mixed. Under immense pressure, hydrogen and helium do not behave like familiar gases. They become phases, layers, and gradients that can shift over time. If helium becomes less soluble in the surrounding hydrogen at certain depths, it can begin to fall. Not fall like rain in Earth's air, but sink through a denser medium like a slow, invisible precipitation. As it descends, it releases gravitational energy as heat. The planet warms itself by sorting itself. A world generating weather because its elements are drifting into new arrangements. You can treat that as physics and be done. But it carries a strange emotional shape. It suggests that Saturn's storms are not merely a response to the present. They are the surface expression of deep interior history of the planet, continuing to change its internal structure long after it formed. Weather becomes a symptom of planetary aging rather than sunlight. This is why Saturn feels like a place where the sun is almost incidental. The sun still matters. It still influences the uppermost haze, the photochemistry that changes colors, the seasonal variations that shift over long time. But the most muscular part of Saturn's climate does not wait for the sun's permission. It rises from below. And it keeps rising because the planet has not finished becoming itself. When the energy comes from within, the atmosphere behaves differently. Storms can be fueled from deep convection rather than surface heating. Lightning can form in layers where water exists under pressures and temperatures that make the concept of cloud feel too gentle. Electrical discharge becomes a consequence of violent vertical motion inside a thick envelope of gas, where particles collide and charge separates, and the planet briefly reveals that even in the outer solar system, thunder is possible. And because there is no solid surface to fracture the flow, no continents, no mountains, no oceans, with coastlines, winds can wrap around the planet and remain coherent for long periods. On Earth, friction and terrain shred patterns. On Saturn, patterns can become architecture. Jets can persist. Boundaries can hold. The atmosphere can develop a kind of memory, where motion today is shaped by motion from long before. This is where Saturn's most unsettling feature appears, not as a single storm, but as an organized refusal to be circular. Near the pole, the planet carries a persistent polygonal jet stream, a pattern that looks like geometry imposed on fluid. It shouldn't last. You expect it to blur. Instead, it holds its shape. A reminder that rotating fluids can lock into wave patterns that seem too clean to be natural. Until you remember that natural includes mathematics, whether we want it to or not. Saturn doesn't need intention to produce a shape. It only needs the right rotation, the right stratification, and the right balance of forces. The result feels like a design, but it is only equilibrium pretending to be art. The deeper you imagine going into Saturn, the less Earth's language helps. Pressure climbs until gas becomes liquid, then becomes something stranger. States where electrons behave differently, where conductivity changes, where matter stops being easily categorized. In those depths, heat transport is not a gentle upward drift. It is a struggle between layers that want to mix and layers that resist mixing. Between convection that tries to overturn the interior and gradients that try to keep it stable. Even the idea of weather starts to fail, because weather implies a thin atmosphere above a world. Saturn's motion is the world. Its climate is not above anything. It is a planet-sized fluid system rearranging itself. So when you see winds tearing across its cloud tops, the sensation should not be that Saturn is active despite the cold. It should be that Saturn is active because the cold is only on the outside. The interior is still paying energy into the system, still feeding motion upward, still generating gradients that need to be erased, still refusing to settle. On Earth, climate is a negotiation between the sun and the surface. On Saturn, climate is closer to metabolism, energy produced within, distributed through layers, expressed as motion. The most direct expression of that is speed. Saturn's equatorial winds reach 500 meters per second. That number is not just a measurement. It is an insult to intuition. It says that an atmosphere can move faster than a human mind expects, even without solar heating as the primary driver, because the engine is internal and the medium is deep and the planet's rotation shapes everything into organized flow. It says the outer solar system is not a graveyard of sluggish worlds. It is a region where different engines run. And in the middle of all this, Saturn remains politely tilted, giving the sun a way to touch it unevenly over time, introducing seasons that play out slowly, not through warmth on land, but through shifts in the upper atmosphere's chemistry and haze. Its axis is inclined by 73 degrees. The tilt is modest compared to Uranus's collapse into sideways rotation, but in Saturn it carries a different meaning. It shows how little it takes to introduce long-term variation, and how those variations don't need to control the climate to still matter. The sun influences the skin, the color, the photochemical layers. The interior controls the muscle. This is what makes Saturn disorienting. It is a world where weather does not behave like weather is supposed to behave, because our definition of weather is provincial. We think storms are responses. Saturn's storms are emissions. The planet is not being heated into motion. It is releasing motion as a byproduct of its own slow evolution. And once you accept that, the rings begin to feel less like decoration and more like a frame for a deeper truth. Saturn is not a static body with a pretty border. It is an active system pretending to be calm, a planet that looks serene from far away, while inside it, gravity continues its work. Layers continue to separate, heat continues to rise, and the atmosphere continues to move as if the sun were only a distant suggestion. In a solar system that seems orderly from the outside, Saturn is a reminder that order can be powered by hidden engines, that a world can ignore the most obvious source of energy and still remain violently alive in its own way, and that the farther you go from the sun, the less you can trust the story that sunlight is the reason anything moves. An invisible engine can power a planet's weather, but gravity can turn destruction into something that looks from far away, like calm design. Saturn's rings are often treated as a symbol of elegance, as if the solar system occasionally chooses to decorate itself. But rings are not decorations. They are dynamical systems made of debris. And debris has to come from somewhere. When you stop thinking of the rings as a picture and start thinking of them as matter, their existence begins to feel less like beauty and more like evidence of a past event that did not end cleanly. Because ice and rock do not arrange themselves into wide, flat, sharply bounded disks by accident. They arrange themselves that way when a body is broken apart and then prevented from reassembling. That prevention is the first hard truth. Near a massive planet, there is a region where an object's own gravity can no longer hold it together against tidal forces. The closer you get, the more the planet's gravity pulls harder on the near side than the far side. If the difference becomes large enough, the object is stretched and stressed until it fractures. This boundary is not a myth. It is geometry enforced by gravity, known as the Roche limit. For an icy moon near Saturn, the relevant Roche limit is about 147,000 kilometers from Saturn's center, a distance at which a cohesive object can be forced into breakup if it passes too close. The implication is simple and unsettling. The rings may be what remains after something that used to be whole wandered into a region where wholeness is no longer stable. Not because it was weak, but because the space it entered did not allow integrity. Once a moon crosses that boundary, the outcome is not necessarily a single clean snap. It can be a progressive failure, fractures, shedding, collapse until the object becomes a stream of fragments that spread around the planet's equator like a wound becoming a bandage. This is one of the solar system's recurring inversions. We look at rings and see order. The history that produces them is likely disorder. A moon disrupted. A comet shredded. A collision that changed an orbit enough to send an object into a fatal approach. We do not know the exact origin for Saturn's rings with full certainty, and that uncertainty is part of what makes them philosophically sharp. The rings can be old, or they can be relatively young. They can be the remains of a moon, or the accumulated residue of multiple events. But whichever scenario you choose, the common element is violence, matter being forced out of a stable configuration into a new one. The new one is not stable in the way we instinctively imagine stability. A ring system is always trying to change. Particles collide and exchange energy. They clump and shear. They grind into dust and then spread. Left alone for long enough, the ring would blur, thin, and evolve into something less defined. Yet Saturn's rings are remarkably structured, bands separated by gaps. Sharp edges, spirals, ripples, features that imply continuous gravitational sculpting. This is where the second inversion appears. The rings may have been born from chaos, but they are maintained by countless small acts of control. Some of that control comes from moons. Tiny shepherd moons can confine particles, pushing them back when they drift, creating narrow rings that remain narrow. Larger moons can carve gaps through resonances, forcing ring particles into orbits that avoid certain regions, leaving empty lanes as if something swept them clean. The gaps are not absences of material because nothing was ever there. They are absences created by gravity, insisting on certain rhythms. The rings are an archive of orbital music, where the notes are small pieces of ice and the harmonies are set by moons you can barely see. Cassini made this harder to treat as metaphor by showing details that don't fit the flat postcard view. The rings are thin compared to their vast width, but they are not perfectly flat. Local disturbances can create vertical structures, tiny walls and waves that rise above the plane, casting shadows and revealing thickness where we assumed there was none. Under the right lighting, the rings become a field of relief, not a sheet. Their delicacy is real, but it is not gentle. It is active, constantly rearranged by gravity. The scale is part of the disorientation. Saturn's main rings extend outward to about 140,000 kilometers from the planet's center. wide enough that you could place many Earths side by side across their span and still not reach the far edge. Yet their thickness is small by comparison, so small that the system feels less like a structure and more like a phenomenon. A pattern that exists because the physics allows it, not because it resembles any stable object we are used to. A ring is what you get when matter cannot become a moon and cannot become a cloud and is forced to remain in between. And the rings themselves are not made primarily of rock. They are mostly water ice, with particles ranging from tiny grains to chunks as large as houses. This composition matters because it makes the rings bright, reflective, and visually striking, but it also carries a historical question. If the rings are mostly ice, then whatever broke apart must have been rich in ice. That points naturally to an icy moon, a body that once had its own orbit, its own internal structure, perhaps even its own geological history. The rings may be the remains of an object that was not trivial, which creates an emotional paradox that is easy to avoid if you keep Saturn at postcard distance. The rings are one of the most iconic landscapes in our system, often used as shorthand for cosmic beauty. But if they are the debris of a moon that was destroyed, then the rings are not a decoration at all. They are a graveyard arranged into a disk, a catastrophe turned into symmetry. Even the ring's total mass, estimated at about 1.5 times 10 to the 19th kilograms, doesn't soften that feeling. It reinforces it. That much material is not the residue of a small accident. It is the remains of something substantial, ground down and distributed. Gravity didn't just break a body. It then refused to let the body return. And the refusal is the key. That is what the Roche limit represents. Not merely the power to destroy, but the power to keep something destroyed by preventing reassembly. A moon too close is not allowed to heal. The fragments collide, but instead of gathering, they are sheared, tugged, and redistributed until the system becomes a long-lived ring. The violence is not only in the initial event, the violence is in the ongoing condition that makes wholeness impossible. So the rings become a lesson about how the solar system can generate scenes that look serene while being built from the denial of stability. Saturn wears its catastrophe as a structure. It is a world whose most famous feature may be the fossil of a gravitational tragedy, preserved not by stillness, but by continuous motion, countless particles orbiting in disciplined paths because the physics of that region allows nothing else. And once you internalize that, it becomes harder to see beauty in the solar system as something separate from destruction. In this system, order and violence are not opposites. Sometimes order is what violence leaves behind. If a planet's rings can be the fossil of violence, then the strangest worlds are the ones that look like they've already been undone, and yet they keep moving as if nothing happened. Uranus is that kind of contradiction. A planet that behaves like the aftermath of an impact, but still fits into the solar system's quiet clockwork with disturbing ease. There is no gentle way to describe its orientation. Uranus is not merely tilted, it is nearly sideways, as if the planet tried to stand up and failed, and then decided to continue living in that position. Its axis is inclined by 77 degrees, enough that the usual language of north and south starts to feel like an inherited mistake. When a planet is tipped that far, seasons stop resembling anything we know. The sun does not rise and set the same way. Whole hemispheres take turns being favored and then forgotten. The geometry becomes personal, almost embarrassing, like a body caught in an unnatural posture that cannot be corrected without breaking something. And yet, nothing breaks. That is the first discomfort. A planet can be knocked into a posture that looks catastrophic, and the system does not fall apart. Its moons continue to orbit. Its rings remain arranged in thin, disciplined structures. The planet maintains an atmosphere, a magnetosphere, a rhythm. From a distance, it looks calm, pale, almost blank, like it has nothing to confess. But the blankness is the confession. Uranus does not look dramatic because it does not radiate much internal heat. It is cold in a way that feels less like an environment and more like a missing engine. It is a world that should be loud, with leftover formation energy, still churning, still emitting, still glowing faintly with interior work. Instead, it appears muted, as if something that should be active has been damped or drained. That muted quality is not a lack of mystery, it is evidence. A planet does not become quiet by accident. It becomes quiet when it cannot move energy upward the way other giant planets do, or when some earlier event altered its interior enough to change its long-term behavior. Uranus is often described as boring, but boredom, here, is not absence. It is a clue that the planet's history might include a loss, internal warmth that never fully recovered, or internal layering that prevents heat from escaping, or a structure so altered that the usual pathways of convection are disrupted. In other words, the calm face may be the scar. Its rings make that scar harder to ignore, because rings are a form of order that should not survive carelessly. Ring particles collide, they spread, they clump, they grind into dust. A ring system is not a static ornament. It is a dynamic environment, always trying to erase its own sharp edges. And yet Uranus's rings show boundaries, narrow bands, defined edges, gaps that look carved, as if an invisible hand has measured where particles are allowed to linger. The explanation is almost insulting in its simplicity. Tiny moons can maintain large-scale structure. A moon small enough to be overlooked can shepherd ring particles, tugging them inward and outward, preventing a ring from smearing into a featureless haze. Gravity does not require grandeur to impose discipline. Even something minor can become a keeper of borders. It is one of the solar system's recurring humiliations. Order is often enforced by the smallest bodies, the ones we did not expect to matter. So, Uranus begins to resemble a place where violence and delicacy coexist without resolving the tension. The planet looks like a collision site. While its rings look curated, it looks like an accident, while its system looks maintained. The more you sit with that, the less impact feels like an explanation and more like a confession the solar system keeps repeating. Worlds become what they are through events that would sound impossible if you described them without evidence. The leading idea is not subtle. Somewhere early in Uranus's history, a massive body struck it, a collision energetic enough to tip the entire planet, not a gentle nudge. Something with the kind of mass that, in any human intuition, should leave the target shattered or stripped. And yet the planet remains. The atmosphere remains. The moons remain. The planet still rotates, still circles the sun, still carries its weight without scattering into a debris field. This is not what catastrophe is supposed to look like. We imagine catastrophe as a failure of continuity, but in planetary history, catastrophe can be continuous. A world can absorb an impossible blow and continue, altered but intact, as if the definition of intact is simply still gravitationally coherent. Take Idin. That forces a different kind of realism. It suggests that planets are not fragile objects awaiting a single decisive trauma. They are resilient bodies that can be radically reconfigured without being destroyed. Their identity is not a pristine state. It is whatever configuration survives. Uranus, lying almost on its side, is not an exception to order. It is what order looks like after something went wrong and nothing intervened to make it right. Even the planet's magnetism carries that sense of misalignment. On most worlds, the magnetic field and the rotation axis behave like they are cooperating. On Uranus, they do not. The magnetic structure is tilted and offset, creating a magnetosphere that behaves less like a symmetric bubble and more like a distorted, shifting region of influence. That matters because magnetospheres are not just shields, they are interactions. They are how a planet negotiates with the sun's particles and fields. Uranus negotiates awkwardly, with a geometry that seems to have been scrambled. The result is a space environment that can be strangely twisted. A long tail drawn out behind the planet and contorted by the sideways spin. It is as if even the planet's invisible anatomy refuses to line up. And still, the system runs smoothly enough that the mind begins to treat it as normal until you remember how far away it is, and how delayed everything becomes. The sunlight that reaches Uranus is not fresh. It is ancient by the standards of a human moment. From the Sun to Uranus, light takes 9 billion kilometers worth of travel before it arrives. That distance is not just a measurement, it is a feeling. It means the planet is lit by a sun that is already slightly older than the sun we see, because the information arrives late. When you look at Uranus, you are looking at a version of the solar system that is not quite now. The further out you go, the more present becomes an approximation. On such a distant stage, you expect sluggishness. You expect low-energy atmospheres that barely move. But Uranus has winds. It has clouds that change. It has motion that refuses to match the weak sunlight. Wind speeds can reach 900 kilometers per hour, which is not a poetic exaggeration. It is a reminder that atmospheres do not require warmth in the way we instinctively believe they do. Motion can be driven by internal heat, by the dynamics of rotating fluids, by the redistribution of energy through layers we cannot see. The planet can be cold and still restless. In fact, sometimes coldness sharpens gradients and makes motion easier to sustain, because the system is constantly trying to equalize what it cannot equalize quickly. The deeper paradox is that Uranus looks quiet in its overall heat budget and yet can still produce dramatic local behavior. That contradiction is not fully settled. It hints that we do not understand the planet's interior well enough to say why it radiates so little heat compared to its neighbor Neptune, or how its internal layers are arranged, or what its long-term evolution has been. Uranus is a reminder that planetary science can describe what a world does without fully understanding why it does it that way. The measurements exist. The causal story remains incomplete. And then there is the simplest destabilizer of all, Uranus's year. It takes about 84 Earth years to complete an orbit. A season is not a mood change from month to month. It is a generational shift. The planet spends long stretches receiving sunlight in ways that would feel like a permanent condition if you lived there. A hemisphere lit for years, then dark for years. A slow swap of which pole is favored. Under those conditions, the atmosphere is forced to respond to patterns that are too slow for our intuition. Weather does not merely happen. It has time to become a climate in motion. Storms and hazes and circulations can be shaped by illumination that changes like a tide rather than a day-night cycle. This is where the shouldn't be upright feeling becomes sharper. Uranus is not upright. It is tilted in a way that looks like it should destabilize. Everything rings. Moons, climate, magnetosphere. And yet, it does not collapse into chaos. It becomes a different kind of order, one that does not resemble the order we grew up with. The solar system tolerates configurations that would look like mistakes in any clean model. It allows the aftermath to become the baseline. There is a quiet lesson in that tolerance, and it is not comforting. We like to believe that systems have preferred shapes stable, efficient, reasonable, but Uranus suggests that stability is broader than reason. A planet can be knocked into a state that looks absurd and still remains stable for timescales longer than anything human civilization has ever survived. The universe does not correct wrong. It merely tests whether wrong can persist. If it can, it becomes the new normal. And once you accept that, the planet stops being a curiosity and starts feeling like a warning about how easily our sense of cosmic order is manufactured. We see 8 planets and assume a tidy hierarchy. We see circular paths and assume design. We forget that the solar system may have been sculpted by collisions, migrations, Resonances by episodes that would make a stable diagram impossible if we watched them happen in real time. Uranus is the evidence that something severe occurred, and that severity did not end the story. It only rewrote it. The unreasonable part is not that Uranus was knocked over. The unreasonable part is that it stayed that way, and nothing came along to fix it, because nothing in the solar system is tasked with fixing anything. A world can remain tilted, cold, and oddly quiet, still carrying rings kept in line by small moons, still moving through space with a calm that feels undeserved. It is the kind of stability that doesn't reassure you. It makes you wonder what else could happen to a planet and still count as surviving. Is Ribald? Uranus feels like a world that has been muted by its history. Its twin, Neptune, proves that distance does not guarantee quiet. It exists to prove that our instincts don't travel well. Neptune is so distant that sunlight arrives like an afterthought, thinned out until it feels more like illumination than heating. The planet sits at about 30.07 astronomical units from the Sun, far enough that daylight sounds like a rumor passed from the inner system rather than a force that can shape a world. And yet, when we finally looked closely, Neptune did not behave like a cold, sleepy object at the edge of the Sun's reach. It behaved like something restless, something that hadn't been informed it was supposed to be calm. The first time Neptune really entered human perception as a physical world, it arrived with a contradiction large enough to be visible even through our limited encounter. Dark storms, bright clouds, bands of motion wrapped around the planet like muscle fibers. A weather system so active it didn't just move, it organized itself into structures that seemed to have intent, as if the atmosphere had decided to become a landscape. The most famous of these was a dark feature that looked like a wound in the cloud deck, a region where methane clouds thinned and deeper layers became visible, creating the impression of a void. It wasn't a surface, it wasn't a hole in rock. It was an absence inside a fluid, a reminder that on these planets, emptiness can be a weather event. Around features like that, winds were measured at speeds that feel out of place so far from the Sun. At high altitudes, they can exceed 1,100 miles per hour. That is not a flourish. It is a number that forces you to stop pretending Neptune is merely cold. Cold, in human language, implies reduced motion. Neptune is cold in temperature, but not in behavior. It is cold and violent at the same time, and that combination is what makes it hard to metabolize as a concept. The planet asks you to separate the idea of energy from the idea of sunlight, to accept that a world can be dimly lit and still aggressively alive in motion. On Earth, we link wind to heating differences. Warm air rises, cool air sinks, pressure gradients form, air moves to erase them. On Neptune, that story is incomplete before it begins, because whatever the Sun contributes at that distance cannot easily explain what we see. The wind speeds are too high, the storms are too coherent. The whole atmosphere feels like it has access to a deeper reservoir of power, which means Neptune is not merely reacting to the Sun, it is expressing its own interior. This is where Neptune becomes stranger than Uranus in a very specific way. Both are ice giants, similar in size and composition, neighbors in the outer dark, but they do not feel like twins. Uranus wears a blank face, as if it has mislaid its heat or sealed it away. Neptune, in comparison, behaves like a planet that still has something burning inside, something that continues to leak upward, driving circulation, feeding storms, sustaining jets that can wrap around the globe with very little interruption. The unsettling implication is that planets that look similar can diverge radically in behavior for reasons we still cannot fully pin down. Not because we lack data entirely, but because the interior physics is hard, layered, and not directly visible. We can watch the skin move and still not know what the organs are doing. There are explanations, but none of them land as comfort. Neptune radiates internal heat, likely a mixture of leftover formation energy and ongoing gravitational processes. The slow settling and rearranging of matter under immense pressure. Inside these worlds, ice does not mean frozen cubes. It means a family of volatiles: water, ammonia, methane, compressed into states that don't resemble everyday matter. In those depths, materials can become exotic fluids, electrically conductive mixtures, layers that convect or resist convection depending on how they are stratified. The planet can contain energy gradients that take immense time to dissipate, and the attempt to dissipate them becomes weather. One hypothesis, often repeated because it is vivid, involves carbon under pressure. Methane contains carbon, and in Neptune's interior, the pressure and temperature may be high enough for carbon to separate into heavier forms. If that happens, carbon could sink, releasing heat as it falls. The way any descent through a gravitational field pays energy into the system. People like to call it diamond rain because it gives the mind something solid to hold. But even if the details are different phases, different pathways, the underlying idea remains. Separation inside the planet can be an energy source. A world can power storms by sorting itself. And once motion begins, Neptune's lack of a solid surface becomes an accelerant. There are no mountains to break the flow, no continents to interfere, no forests or frictional landscapes to chew up wind into turbulence the way Earth does. Patterns can persist. Jets can remain coherent for longer. Storms can travel without being torn apart by obstacles. On Earth, weather is constantly being interrupted. On Neptune, weather can become a long-running structure, a moving architecture built from pressure, rotation, and deep heat. The Great Dark Spot, if you let yourself think of it not as an image but as a phenomenon, captures that. It wasn't simply a storm, it was a large-scale organized absence, surrounded by bright companion clouds that formed and dissolved as the system evolved. And it was large enough that its longer dimension was about 13,000 kilometers, which places it in the category of storms that stop feeling like weather and start feeling like a planetary feature. When something in an atmosphere reaches that scale, you can't avoid the thought that the planet is not wearing storms like temporary moods. The storms are part of how the planet expresses its physics. But Neptune won't let even that become a stable story. Those dark storms do not necessarily last like Jupiter's famous vortex. They can form, drift, change shape, and disappear, replaced by others. This makes Neptune psychologically difficult in a different way than Saturn. Saturn's dynamics can feel like a machine: persistent bands, a long-lived polar pattern, an atmosphere shaped into structure by rotation and internal heat. Neptune's dynamics feel more like a living system that refuses to hold still long enough to be categorized. The storms are real, but the identity of the storm is not permanent. Neptune gives you evidence and then withdraws it, as if reminding you that observation is always catching a moving target. That impermanence matters philosophically because it denies the viewer the comfort of a stable symbol. Humans love to attach meaning to a single enduring feature. We want the storm to be a landmark, a character, a thing we can revisit across time. Neptune does not promise that. It offers a storm as proof that the atmosphere is powerful, then takes it away, leaving behind only the deeper question: what kind of planet produces giants and then erases them? So the paradox deepens. Neptune is cold, far, dimly heated by sunlight, and yet it generates the strongest winds we've measured. It hosts storms so large they belong on the scale of worlds, and yet those storms can vanish as if they were never owed to us. It looks smooth and blue and calm from a distance, and then, closer, reveals an atmosphere that behaves like it is being pushed from underneath. And because Neptune sits at the edge of the familiar, it changes the emotional meaning of the solar system itself. The farther you go, the more you expect quiet. Neptune teaches the opposite. It suggests that distance does not guarantee stillness, and that the sun is not the only storyteller in its own system. Planets keep their own histories. They carry their own engines. Some of them go silent. Some of them continue to move as if the darkness is not a constraint but a canvas. If the solar system is supposed to be an orderly arrangement where energy fades with distance, Neptune is one of the places where that belief fails gently but completely. The wind does not apologize for the cold. The storms do not wait for the light. The planet simply continues, far out, proving that our expectations are not laws, only habits that survive until the next world breaks them. If order can be the fossil of violence, then the solar system stops being a comforting diagram and becomes something closer to a record of near failures that happen to persist. And once you see that, the feeling doesn't leave when the facts end. None of this makes sense in the way we want home to make sense. Not because the physics is broken, and not because science is powerless. The paradox is subtler. The physics is consistent, and science can explain each piece. Yet the system still feels unreasonable when you place those explanations next to each other. We carry an instinct that reality should be stable, fair, and predictable if we understand it well enough. But the solar system is not built to satisfy instincts. It is built from interactions, collisions, migrations, resonances, slow leaks. Internal engines shutting down, and the outcomes we live among are not the logical outcomes. They are the outcomes that survived. Earth kept oceans for billions of years, not because water is rare, but because the planet happened to maintain pressure, temperature structure, geology, and feedback long enough for water to remain surface water. Mars once had environments that feel almost generous, and still lost the conditions that would let those environments matter. Uranus was knocked sideways and kept going, as if damage is just another stable configuration. Saturn's weather ignores the sun's weakness because the planet runs on internal heat and long-term gravitational work. Neptune is cold and still violent, because motion is not obligated to fade with distance. Mercury sits too close to the sun and still holds things we assumed it would have lost, because history can override location. Jupiter can scatter, starve, deliver, and shield, because a single massive body can turn the entire system into a coupled game where every orbit is influenced by another. And the sun, the source of life's energy, is also a timer, because a star is a process, not a constant. None of this is absurd because it violates science. It is absurd because it violates the expectations that science does not promise to fulfill. We confuse comprehension with comfort. We take a successful explanation and assume it should make the outcome feel inevitable. But inevitability is not the same thing as explanation. An explanation tells you why something happened given what happened before. It does not tell you that it had to happen, or that it was the most likely path. The solar system keeps forcing that distinction on us. It says, yes, you can understand the mechanism, and no, that won't make the result feel safe. The deeper reason it matters is that our entire sense of normal is based on a short slice of time. Human history is thin compared to planetary history. Civilization is thin compared to stellar history. Earth is about 54 billion years old, and our species has existed for a fraction so small it barely registers on that scale. When you place your life on that timeline, stability becomes a local illusion, not because the world is about to collapse tomorrow, but because the concept of the way things are is mostly the way things are right now. The solar system is a place where right now is a moving target. This is why the phrase "mostly figured out" is dangerous. It invites the mind to think of knowledge as a completed map, but what we have is closer to a set of workable stories constrained by evidence, always subject to revision as new data arrives. We can measure Uranus's tilt precisely and still not fully know the interior history that made it that way. We can watch storms on Neptune and still argue about what drives their deepest energy. We can model Jupiter's migration and still debate which path best matches the architecture we see. We can describe the Sun's future with confidence in broad strokes and still wrestle with details of timing and planetary response. The uncertainty is not a failure. It is the honest shape of knowledge in a system this old and this dynamic. So why does it matter? Beyond curiosity? Because the solar system is not a distant subject. It is the context of our existence. It defines the range of futures Earth can have, not through prophecy but through constraints. The Sun's evolution sets the long-term limits of surface habitability. The presence of Jupiter influences the pathways of comets and asteroids over time. The existence of Earth's magnetic shield changes what the solar wind can take. These are not abstract stories. They are the conditions that allow you to have a breathable sky and a stable ocean cycle in the first place. And there is another kind of meaning, quieter and more personal. When you realize how easily worlds lose what seems essential, how a planet can dry out, how an atmosphere can be stripped, how a system can be rearranged by a migration that had no intention, you begin to see Earth differently. Not as a guaranteed stage, but as a temporary configuration held by balances that can fail. This does not make Earth less valuable. It makes it more specific. It shifts the emotional posture from entitlement to attention. The solar system is often presented as a family portrait: 8 planets, predictable paths, an orderly structure, but it is closer to an archive of accidents that happen to stabilize, an archive of near ruins, an archive of narrow margins. If you want a single number that captures how narrow, consider Earth's distance from the Sun, about 149.6 million kilometers. It is a clean figure that gets taught early, and it sounds like a location, like an address. But it is also a balance point in a larger system that can drift, brighten, rearrange, and end. The distance is not a guarantee. It is one variable in a relationship that changes as the star changes. This is where the title becomes less of a provocation and more of a diagnosis. These wonders make no sense because human intuition expects the universe to reward coherence. We want the rules to produce outcomes that feel orderly, and we want home to be the natural result of those rules. But the solar system suggests something else. The rules are indifferent. And coherence is something that sometimes emerges for a while. Life, then, is not embedded in cosmic order as a destined centerpiece. Life is something consciousness negotiates inside a system that does not care whether negotiation succeeds. That may sound bleak if you mistake indifference for hostility, but indifference is not hostility. It is simply the absence of a promise. And the absence of a promise does not erase the fact that, for now, we are here, against a background of worlds that failed to hold their conditions. We inhabit one that still does. Against a background of future constraints, we occupy a present that remains workable. The final feeling is not triumph. It is proximity. You feel closer to home because you can see the mechanisms that keep it intact, and you feel less certain of it because you can see how contingent those mechanisms are. The solar system does not offer reassurance. It offers perspective, that stability is often a short story written inside a long, chaotic book. And if there is one truly unreasonable thing about it, one thing that never stops being strange, even after all the explanations, it is this: we are here to notice the contradictions. We are here to ask the question,